Have a nice day, ladies and gentlemen, and all my friends from industry. I'm happy to see you here, and as a tradition, this White Bandgap Forum runs for a long time here at PCIM. And today we have Alfred. Alfred will co-moderate it with me. We have an hour for SiC, and questions and cross discussions will be at the end, plus the possibility that you can join the presenters at their dedicated booths. Thank you so much, and let's start. The first one is the gentleman from Fuji, Bijan Khair. Khair, it's you. Okay.
Thank you. So it works? Okay. So, can I start? Yeah. Okay. Yeah. Hello. My name is Bijan Khair, and I'm working for Fuji Electric Europe as an application engineer for Semiconductor Technical Division. And today I have the pleasure to introduce our third generation of silicon carbide chip technology. Therefore, we will start with the improvement of the third generation silicon carbide chip technology, then continue with optimized packaging technology. Then I will cover some points about third generation silicon carbide application, and finally at the end some points about the lineup of industrial and automotive. So before I will proceed with the features of the silicon carbide third generation chip technology, let me show you the history of silicon carbide chip technology. Fuji Electric started at 2016 with the planar structure. Then 2 years later, Fuji Electric released the first generation of trench gate structure that has significantly reducing the ROHM. You can see from 7.7 to 3.5 milliohm per milliohm square centimeter. Then in 2022, Fuji Electric released the second generation of silicon carbide chip technology with trench gate structure. And now for 2025, let me introduce the third generation of silicon carbide chip technology with only 2.3 milliohm square quadrat centimeter for industrial applications or industrial modules and 1.9 for automotive. And the Fuji third generation silicon carbide trench gate MOSFET features are reduced ROHM at low and high temperature. Schottky barrier diode are no longer required because the body diode is fully able to handle the energy. Then high reliability, stable VGS, no bipolar degradation because there's no Schottky diode, and good trade-off between ROHM and VGS. And we will provide the modules with the voltage classes for industrial 1.2 kV until 3.3 kV, and for automotive 750 until 1.2 kV. So let's come to the optimized packaging technology, optimized internal structure with parallel PN. PN, you can see it here for industrial module, and that means we can provide here low stray inductance, also for industrial HPNC modules and also for the automotive modules. So Fuji third generation silicon carbide trench gate MOSFET will be used in industrial and also in automotive. The industrial target is renewable energy, hydrolyzers, battery storage system, UPS, and fast charging. And for automotive, proposals, air conditioner, onboard DC-DC, and onboard charging. So now I will introduce the lineup of industrial modules. You can see here all our industrial modules based on silicon carbide chip technology. And due to the time limitation, I will introduce only our highlight product, HPNC, with 1.7 kV until 3.3 kV voltage rating and current rating of 850 until 1800 amp. This package we have with 2-in-1. We have also other packages with 6-in-1. And for automotive, we have 2-in-1 combined in 6-in-1 module with the voltage class of 1.2 kV and a current rating of 450 amp until 1000 amp. We can also combine 4-in-1 to combine this for in 12-in-1 for 3-level module with a voltage class of 1200 volt and 660 amp. Of course, we also provide our discrete modules with silicon carbide chip technology, with the latest silicon carbide chip technology, with the voltage classes of 750 volt until 1200 volt, and R1A or add-on of 10 milliohm until 80 ohm. So, if you have any question or want to see those modules, you can visit us at Hall 7. Thank you for your attention.
Thank you very much. I really appreciate your speech, being speaker number 1, talking about generation number 3. So it's almost time for speaker number 2. But before, I would like to tell you something about our magazine. It's Bodo's Power, founded by Bodo. You saw Bodo's already. And my name is Alfred Vollmer. I'm the editor-in-chief of Bodo's Power Systems. Now it's time for speaker number 2 for Eugen Stumpf from Mitsubishi Electric.
Good afternoon. Next 5 minutes you are with me, with Eugen Stumpf from Mitsubishi Electric. The name of my presentation, Silicon Carbide, is in our hand because preparation is done in heavily discussion with my lovely colleague Shori Idaka. Which car will represent Silicon Carbide? Will be Supercar or Toyota Corolla. Result is Silicon Carbide is with us. Performance is clear. Price projection is there. Reliability more or less there. So Silicon Carbide is with us. I don't want to talk about future of Silicon Carbide. I would like to concentrate on where we are today, about present situation. So we are in great exhibition PCM. I would like to use this opportunity to show our portfolio. We start with relatively low power with slim dip. Go to the relatively high power for 3.3 kilovolt devices developed for traction application. The portion of industrial and renewable energy application is the biggest one. Following by automotive application with a dual power module and 6-in-1. Additionally, we offer chips for automotive purpose. The most fresh product is a Slim Deep IPM. Here we developed a hybrid Slim Deep IPM and full SiC, which is compatible with today's available Slim Deep package. In best case, with silicon carbide full SiC Slim Deep IPM, we can reach 18% less power loss. Please allow me to present you 3 papers. In this PCM, all 3 papers are about silicon carbide. The first one is about Slim Deep IPM, about a hybrid one. Hybrid means we will use in parallel mode reverse conducting IGBT silicon, and in parallel is connected MOS FET. Silicon carbide for switching, we use silicon, switch on and switch off. And for steady state, for conduction, we use MOS FET. And this will contribute a lot for partial load which is so important, for example, for aircon application. Next paper is about higher power, about LV100. This paper explains how to avoid oscillation without the acceleration of silicon carbide without using higher RG. And number 3 is my favorite. It is about reliability, about how to use and what will be impact in case we use a body diode, current flowing through the body diode, with which impact we have to live. And in my understanding, today's bottleneck of using silicon carbide is still unknown reliability. It is not high initial price. Here I'm again with engineers from Semicron Danfoss that high initial price is a fairy tale. Most frequent question in our meetings is how is situation with 8-inch production. I would like to update you. We're on schedule. Factory will be built by end of this year, and beginning of 2026 we will start operation. This is my last slide. I would like to invite you to our booth. We're in hall 7 because I have here 5 minutes. Probably in our booth we will have 10 minutes without any interruption. In my opinion, is still the same from the last year. The best location to discuss silicon carbide is a brewery. We have no price pressure and we have no pressure from compliance. Thank you very much.
But now our next speaker will be Pierre Delatte from Cissoid.
Hello, good afternoon. So I'm going to present a SiC inverter development ecosystem. So at Cissoid, we work on silicon carbide since 2011, starting with gate driver and I-rail packaging. In 2016, we introduced our first intelligent power module. And today we are offering hardware and software solution for the development of complete SiC inverters. So what we are offering is first intelligent power module, combining the power module and the gate driver. On top of this power module, we have added a control board to make what we call an inverter control module that you can easily use inside our inverter reference design together with Intel motor control software. Regarding the IPM, so we are offering 1200 volt 3-phase power module with different current ratings, supporting high switching frequency and offering both pin-fin and flat base plate for the cooling. So our inverter control module is adding a control board based on Intel adaptive control unit. And on this microprocessor, combining a ARM core together with programmable logic for fast reaction to fault events. We are running the adaptive control app software from Intel Automotive that is implementing advanced control algorithms for motor control with supporting field-oriented control regulation and different scheme for the modulation. Our inverter platform offers a ready-to-use hardware solution to run Intel adaptive control app and its high-performance OPP modulation. Optimized pulse patterns allow to optimize the complete motor drive, able to achieve high efficiency and high power, especially in the high speed and torque region. So with our reference design that can support peak output power up to 350 kilowatts, high switching frequency and high power density, we can achieve power efficiency in excess of 99%. And so here you have an EPTO for electric power takeoff, which is a good use case of our customer Hydraulic building a complete system around our inverter control module, achieving a total efficiency for the motor plus the inverter of 94%. And so to conclude, at PCIM we are announcing a new partnership with EDAC, which is a leading company offering engineering services. And with them, we plan to further support our customer in the development and integration of a SiC traction inverter. Thank you for your attention.
Thank you very much, Pierre. Pierre Delatte from Cissoid. Our next speaker will be Dr. Evangelos Theodossiu from Vincotech. Evangelos, the stage is yours.
Thanks a lot. Hello and welcome to my presentation, in which I would like to give you a short overview about our latest approach in silicon carbide and how we address this to the application segment megawatt charger. With its remarkable physical and electrical properties, silicon carbide revolutionized the industry, various industry in the last years in the application markets in terms of efficiency and power density. Looking in the three main focus application markets from Vincotech, we see on the left side solar, for sure, from the very beginning, silicon carbide content, specifically the combination hybrid IGBT with silicon diode was developed from the early beginning. Then the industrial market, which at the moment with new regulations and standards are pushing the systems like pumps, servo drives, compressors to meet higher and higher efficiency levels. We will see the silicon carbide content to be more and more demanding also for these applications. And last but not least, and this will be the application segment that we would like to stress today, is the charging, and where from very beginning silicon carbide MOSFET and diodes were the devices of choice. And let's focus for this presentation now on this new megawatt charging application segment. What we see today, we see a lot of many key suppliers for manufacturers for megawatt chargers. They offer the megawatt charger systems, but they are using the infrastructure, the existing infrastructure for fast charging systems. Means these chargers are developed on a modular design. They have power units for 50-60 kilowatt, which are stacked up to megawatt, and then we see for the AC-DC stage, this is connected typical 3-phase 400 volt grid, and then for the DC link we have this 800 volt. For this kind of systems, what you need, the 650 volt and 1200 volt SiC MOSFETs are well suitable and already used. But what we see here, eventually, as the next generation megawatt charging systems is rather a DC coupled system at 1500 volt, which is used not only to increase the power but also to simplify the integration of renewables on also energy storage systems. What does this mean for the? We will see also for the PFC, centralized PFC, and or maybe also solid state transformer, which is directly connected to a mid power grid, and also a DC-DC stage, a modular DC-DC stage distribute the charger power. What does this mean now for the power electronics? Means also that the 1200 volt silicon carbide components are not suitable anymore, not sufficient, so we have to go to the next level. For instance, 1.7 kilowatt, but even better for a higher safety margin to the 2.3, 2.x kilowatt devices. Let's focus now just for the next performance and application benchmark part of it, what I'm going to show you. Let's focus on the AC/DC stage, and let's take as example a typical two-level active front-F application where this is addressed with a half bridge. Of course, this kind of AC/DC stage can be addressed with a three-level topology like a T-type, what you see on the top. So what we see here is the performance benchmark, focusing mainly on the static losses between a 1.2 kilovolt versus a 2.x kilovolt silicon MOSFET from two different suppliers. On the left-hand graph, you see the dependency of drain source voltages from the drain current, and on the right graph, we see the on-resistance dependency on the different operation temperatures. What we clearly see here is that the on-resistance dependency of the temperature on the temperature is for the 2.x kilowatt silicon MOSFETs much higher. I would say higher than compared with a 1.2 kilovolt. And as we can see here on the right graph, you see for instance for the 1.2 kilovolt we have a factor 2, but if you go to the 2.x, depending on the technology, depending on the supplier, then we have a factor up to 2.9. And this is a factor, and this is a fact that we have to take a little bit more effort and to see how we can keep the chip cooler in the application. And this can be because this helps to reduce the static losses. How this can be done, for instance, if we use high thermal conductivity substrates like aluminum nitride or silicon nitride. And on the other hand, this will also lower the thermal stress, which improves the reliability of the module and also extend the lifetime of a silicon carbide power module. Let's move to the application benchmark. For this application benchmark, we took as a test vehicle our 1.2 kilovolt existing 1.2 kilovolt half bridge module, and we compared with a new launched 2.3 kilovolt half bridge module. Both modules are developed with a generation 3 silicon carbide MOSFET from the same supplier and have on resistance at 25 degrees of 8 milliohm. So what you can see here is we clearly see again that on the left graph, you see here the output current. For going to 2.3, you have the double current without compromising efficiency. On the left graph, you see again what we discussed, that going to aluminum versus aluminum oxide, you will have a much better, so you will have lower static losses, for instance, if you, and this effect is more interesting for the 2.3 kilowatt. So, and this is again the summary, and as the last slide, the outlook is, of course, how we are going to further support this next generation megawatt charging is for the AC/DC stage. We are planning to develop also a three-level T-type with this 2.3 kilowatt MOSFETs, and of course also for the DC/DC we will have also a H-bridge based on this 2.3 kilowatt SiC MOSFETs. So thanks for your audience, and we will be happy if you drop by our booth and have a short discussion about how we can support you for your next generation megawatt charging systems. Thank you.
Thank you very much, Evangelos Theodossiu from Vincotech. Now it's time for our next speaker. He is from ROHM Semiconductor, Aly Mashaly. And well, we are listening, and here you get the microphone.
Yeah, good afternoon, ladies and gentlemen. My name is Aly Mashaly. Just give a comment to the presentation from Vincotech before. Interesting application with a very big high demand of power, but we see this also in different other applications, not only in the charging of the EVs, but also data centers. You see nowadays a trend for AI, thousands of terawatt hours what we need it in near future, which would mean that the demand for real clean and green energy is today mandatory than ever before. Therefore, I'm personally proud to go directly to this slide to show what have been we working in the last 5 years intensively with our customer to show such use case of 7.5 megavolt ampere solar inverter with this power module from Semicron Danfoss and introduce our 4th generation 2 kV SiC MOSFET to solve this, this application. What we have introduced here, this is a feature of our silicon carbide MOSFET, and with some feature here, it's a 22 milliohm at 25 degree, but it's a 2 kV power MOSFET, and also investigate the cosmic ray radiation. It's a very key physical parameter what need to be tested in such a very high voltage applications. So that's what we have achieved. Of course, we have several key examples being shown in our booth in hall number 9. But what we work as next, we are still committed to silicon carbide, introducing the 8-inch what I introduced last year, so increasing also the production capacity in our fabs and developing the new generation. So the previous slides showing the 4th generation. Now I would like to show you some slides about the 5th generation, but we also work in developing the 6th generation in parallel. So here, the comparison between 4th and 5th generation here in the output characteristics, you can see that 41% reduction in the voltage drop at the same current, and the at temperature behavior means the temperature dependency of the silicon carbide is a very important physical parameters need to be included here. That's at higher temperature, the 5th generation showing a much better thermal performance than the 4th generation. From switching characteristics, also we see here some benefits there, and also reduce the issue of oscillation. So it's a smooth switching device. Moving forward, so if we really look what is the next step is definitely the package, and it's already proven that this package maybe in the early generation of silicon carbide have been investigated, but it's proven we have to work on something better, and therefore introduce such power modules. Here introduce our TRC drive. We have a real case in our booth with the 4th generation and power module multi-type module here. And in the 5th generation, we're gonna achieve in the same side of the package much higher current rating. A new power module here, the HS dip. It's mass-produced today. We finalized the qualification with this one with a little bit higher power, so it's fit for onboard charger application, for example, and here with a different type of topologies which can be integrated in the same package. Just to show a comparison here of the package, comparing to the topside cool package, how much saving we can achieve here, the same power rating and better thermal performance for the same power and the same in package compared to topside cooling package, but also with the what's common now in the industrial, that we reduce also the size of the module. And that's all. Yeah, if you have any question, please feel free. Thank you.
Thank you very much, Aly Mashaly from ROHM Semiconductors. You're all very, very fast. Very condensed. That's good for you in the auditorium. Our next speaker is Peter Friedrichs. Peter will receive a microphone now, and we will be listening to Infineon.
Thank you very much. Yeah, also a warm welcome from my side. I would like to share with you in the next few minutes, as the title says, some new additions to our silicon carbide device portfolio. Let's start with a journey which we already announced last year. This is the rollout of our recent Generation 2 based silicon carbide product portfolio. We started initially with a lineup targeting at 1200 volt, 650 volt on the more traditional packages like TO247 or D2PAC. Last year we also announced the D2PAC 7-lag portfolio in 400 volt. What now starts to take off more and more is a family of packages based on topside cooling solution. So this is really a very powerful answer to the limitations of traditional surface mount devices regarding the thermal handling performance. So these packages enable now to address extremely high power handling capabilities, which typically have been possible in the past only with through-hole devices. So we have an increased power density. Topside cooling now really becomes manageable. There's enough experience at application engineers available how to manage height differences, etc. So it's taking off. Of course, we come along with higher efficiency, the option of integrating half bridges, and in total, with the abilities now offered with topside cooled devices, the whole system size can be reduced, shrinked. Also, the total weight is possible to reduce. Coming now to the module world, we have now introduced a new flavor of our already well-known easy platform. Outline is more or less the same. Dimensions are equivalent to the previous generations, also the pinouts. However, there's a couple of very interesting technological additions in. One is mentioned here. We are working now with a new plastic material, a new silica gel. This gives us the opportunity to increase the temperature ratings to 175 continuous and 200 degrees C for overload. Also, higher isolation voltages become possible. And together with the fact that we have now also new press fit pins available, which double the possible current via one individual pin, this module platform now becomes even fit for voltages, blocking voltages up to 3 or 3.3 kV. As usual, we have different substrate material options in place, aluminum oxide and aluminum nitride. The latest chip generation based on Gen 2 technology is in. But the most important technology change in this platform is the introduction of DOTXT for the chips inside the package. And this goes back to the title, Designed to Last. The technology is known for offering an extremely high power cycling capability, which is an essential ingredient for storage application, for EV charging, etc. And now with copper-based metallizations, copper bonding technologies, and sinter-like die attach, basically you cannot kill this module anymore in power cycling. And of course the target applications, the most important ones are listed up here. EV charging, energy storage, onboard charging are the ones which dominate today the market. The others like e-aviation and UPS will follow, same for wireless charging. Statuses, engineering samples are available now, and next quarter mass production will start. Yeah, regarding our production capabilities and the transition to 200 millimeter, the pilot projects are all on track. We have a very good baseline regarding material supply. Yields are today already adequate or even better for 200 millimeter compared to 150. The phase over from 150 to 200 millimeter is ongoing. It's going to be even accelerated now in Villach and Kulim. We expect about 3 years until we can finish this one. And timeline for products, the rollout started already in Q1 this year out of Villach. Next products will follow in Kulim. And also the major new chip developments already run on 200 millimeter. Yeah, then two more things we are very happy to announce. First of all, entering the new era of power distribution, especially protecting power distribution by solid-state circuit breakers with JFETs. So you are all invited to visit our booth to learn more about the JFET technology. It enables basically the implementation of smart breaker systems in DC grids especially. We are offering a lineup is down to 1.5 milliohm at 750 volt and 2.3 at 1200 volt. It's all possible to integrate and to scale based again on the topside cooled packages I already introduced. And why JFET robustness and reliability are extremely important in this application. And here the JFET with its current limiting feature offers extraordinary performance. Also RDS on for a JFET can be significantly lower than for a MOSFET. It's a normally on component where no channel contribution is left, and therefore compared to MOSFET-based solutions, just as an example, 10x TO247 now can be realized in 4 times QD-PAC. We will start with 750 volt and 1200 volt based devices, and the target applications are listed up here. So it's all about solid-state protection in distribution networks, plus battery disconnect switches for automotive applications. Yeah, and last but not least, we are also able to announce today a first step into a next era of power density enabled by silicon carbide, and this is a combination of trench MOSFET control systems with superjunction drift zones. We expect here about 40% reduction in horizon times A. This is what you can read also in a press release published yesterday under the label TSJ, Trench Superjunction. This technology was announced. The first products, and this is a very specific target which we start with, is coming in this ID pack, inverter discrete pack for automotive drivetrain applications. It's a scalable concept able to serve 80 kilowatt up to 800 kilowatt by easy paralleling. And the benefits, of course, it's an increased power density with a significant reduction in horizon times A. We have this much higher current handling capability per package. That means less paralleling required. And the products we plan after the introduction of the lead product, it will be a gradual expansion of the portfolio, combined not also with other new generations later on. But it will include, of course, discrete molded frame-based modules, bare die, step by step. Thank you very much.
Thank you very much, Dr. Peter Friedrichs from Infineon. And we had a little raffle where we found out the order of all the individual speakers. And the speaker whose name started with W is the last one. This is Guy Moxey. No, that's the company, sorry, from Wolfspeed is Guy Moxey from Wolfspeed. Sorry, I got a little bit confused, but he won't be, and I hope you will be listening to him.
Ladies and gentlemen, good afternoon. Guy Moxey from Wolfspeed. So 8 presenters here today, and I counted 5, maybe 6 new generations. This is a really good thing, not only for, of course, the market and our customer base, but it's a really good thing about the maturity of silicon carbide. Those of you who have been around long enough, and there's a few of us here that went through the silicon world, you know, if it was numeric, people are on generation 8, 9, 10, 11, 12, 13. If it was the alphabet, people are on generation M, N, O. Each generation, why do you do a new generation? Because it's better than the last, okay? And when I say maturity in silicon carbide, we are now, as you saw here today, getting to the level where people are confident in the maturity of the technology. But what does this mean? We haven't just done it because it's better than the last one and because we can. If you think back to silicon, as you progress through the generations, these headline technology steps, RDS on, switching loss, yes, of course. But as you progress through the generations, you start working down the data sheet because you have the confidence in the maturity. You then look at the second order parameters and start optimizing them because you've got confidence. So my colleague Ali pointed out in his next generation that they're working on a Gen 5. We are now starting to look at, as a technologies provider within the industry, these next level of subtleties. You know, the American phrase or the European phrase, one shoe fits all, is now no longer applicable because we are mature and confident in our ways. So yes, the headline, lower RDS on. Of course, each generation you get lower RDS on. And by the way, we're not having a trench versus planar debate now, which we could do for hours. But, you know, trench, planar, RDS on over temperature. Quite an interesting, spicy point to remember. Planar is still that lower RDS on at working temperature. New generations mean lower RDS on. There's your I squared R, headline, ticked. But then, now, yes, let's look at that second order parameter, that optimization. What do most silicon carbide switches do? They hard switch. And an inverter drive for an EV, it's a hard switched inverter. In a PFC for a data center totem pole, it's hard switched. Yes, in a DC to DC, we're soft switching. But now But Wolfspeed, we have the confidence in the maturity of our next generation that we can start optimizing around hard switch versus soft switch. Different shoe. You got a shoe for dancing, you got a shoe for lifting. So, you know, soft body diode. It may be insignificant if you're soft switching, but when you're freewheeling through your inverter, it makes a huge difference. And yes, a new technology comes in, and here we're actually benchmarking. This is not a line card discussion. This is what actually happens in that system. You've got an incredibly fast technology in silicon carbide. Competition A's latest and greatest. It's like an untamed animal. It's really fast at switching, but look at the impact it gives you. You've got to slow it down. So when you have a new generation and you're confident and mature in that generation, you can optimize. So you design it right. There's little point in having a new generation and then having to slow it down. It doesn't even perform within the datasheet parameters if you use it at their recommended operating conditions in hard switched. You violate by 300 volts. Think of the EMI. Think of the problems that you're getting. So why don't you bring a new generation out that does it right from the start in these second order parameters as well as the headlines? Body diode, soft switching, Eon. Let's just look at some of these parameters when you get down into the details, because now this industry is confident in its maturity to offer technologies that can solve the problems. So yes, RDS on over temperature, soft body diode, turn on losses, reverse recovery charge. This is where next generations you're going to see really making effects. It's great because now you can see what silicon carbide can really do. You know, we've been doing it for 37 years, and I'll have the argument with Ali all the time. We do. Who came out with the first MOSFET? We always debate this. That was 15 years ago. So now we actually have products collectively here that can really address the problems that you have in hard switching, in soft switching, in synchronous boost, in non-synchronous boost, with short circuit. That came up in the detail as well. We're getting there. We've got there. So generation 4, and let's just put it in a system. Let's take a 22 kilowatt AFE, a DC charger, turn it round. You've got a 22 kilowatt inverter for a data center cooling. Let's do some topical applications. You look at those second order parameters and they get you watts. They reduce those losses, switch by switch. And yes, there's some great brand new technologies out there. We saw 6 of them today. There's many more. But let's look at those details, because maturity and confidence gives you those details in the new technologies. Thank you.
Thank you very much, Guy Moxey. Thank you, Wolfspeed. And thank you all for being here. But you also have now got the possibility for a Q&A session. And we will be walking around with a microphone, and Bodo will be handling the Q&A session. Who's got a question, please? Feel free.
Questions? There should be questions. Ladies and gentlemen, we saw a great progress. We have a long tradition here, and I would love to see some cross discussion. If there is no question, I would thank you all for being here. Keep in mind, GAN session will, what time?
At 2:15, we would like to say hello to you again for our GAN session.
So, who stays here will see the GAN session, which is the same format, and we would love to have you here for the next session. Thank you so much. And as it's always mentioned, stay tuned. My magazine will give you a monthly update what's ongoing in the gun and SiC industry. Thank you so much.